Episode 2, Grid and Integers. Let's recap the problem statement. We should check if there exists a grid of given size such that all the elements in the grid are non-negative, and for every 2 by 2 subsquare of the grid, the sum on this blue diagonal is equal to the sum on this red diagonal. Also, some of the elements of the grid are already given and the integers in this range. We are only asked for a yes or no answer. We do not have to print the construction, and well, it would be hard to print the construction because both sides of the grid can be up to 100,000, so the product is very big. So the area of the grid is very big, and also the number of elements that are given is also up to 100,000. On the left here you can see samples from the problem with changed values. So in black the given numbers, in blue the numbers that we can fill in to satisfy all the conditions. So for these two samples the answer is yes, and for other three samples the answer is no for different reasons. So for this sample, just second condition is not true. 0 plus 2 is not equal to 3 plus 1. For this sample, we could put something in this free cell to make the second condition to be true, and it has to be -1, but it is negative, so it is bad. And in this last sample, if we look at the left 2 by 2 square, we have to put 4 here, and if we look at the right 2 by 2 square, we have to put 3 in this cell. Well, each cell should have only one exact integer, so it is not possible to satisfy the second condition for both 2 by 2 squares at the same time. The main property we will be talking about is this sum of diagonals in 2 by 2 squares, and this property is called quadrangle inequality. And matrices with this property are called Monge arrays or Monge matrices. I'm not sure that is how it's pronounced, but it's French, so should be Monge. Well, in this problem, it is not inequality, it is equality. So the sum on the diagonals should be equal. But let's talk about inequality first. So this is the quadrangle inequality. So for every 2 by 2 square in the grid, the sum on the blue diagonal should be at most the sum on the red diagonal. This property, like having quadrangle inequality, is connected to dynamic programming optimizations such as divide and conquer optimization, Knut optimization, and smoke algorithm. You can find more about that connection in the description, and we will talk a bit about why it is why can it help with calculating something with dynamic programming. Okay, let's prove something. A lot of letters here, but it's very easy actually. Let's look at this 2 by 2 square and this 2 by 2 square. From the first one we can see that a plus d is at most b plus c, and from the second c plus f is at most d plus e. We can sum up these two inequalities and get this inequality, and we can see that both of them have c and d in summants, so we can cancel them out, and we will get a plus f is at most b plus e. A and f, b, e. So these are corners of this 2 by 3 rectangle. Then we can add this 2 by 2 square in the same way, and we will get inequality about corners of this 2x4 rectangle. But then we can also stack those rectangles vertically, like this, and applying the same method, we can get that this inequality about sums in corners should hold for any subrectangle of the matrix. So like for any two rows and any two columns, the numbers on the intersection, the one in the upper left corner and the one in the lower right corner, their sum should be at most the sum of the other two. How does it help us? Well, let's say that Ci is the position of the leftmost minimum in row I. We want to prove that if the matrix has quadrangle inequality, the positions of those leftmost minimums are non-decreasing. So if we start in the first rows and move to the second, third, and so on, we will only move to the right. There can be equalities, but we cannot go to the left. We will see why leftmost is important. So the proof will be by contradiction. Suppose it is not true, then there should exist rows I and j such that their minimums are compared incorrectly, and we can look at the positions of those rows and those minimums. And since we assume that Ci is greater than Cj, they are in this order. And we will obviously look at the corners of this rectangle, because we know that Ci is minimum in row I and Cj is minimum in row j. We know some inequalities about the elements. And since Ci is the leftmost minimum, the value to the left should be strictly greater. And Cj is one of the minimums in row j, so the value to the right is at least as big. So we get these two inequalities, we can sum them up. One of them was a strict inequality and the other was non-strict. So when we sum them up, we will get a strict inequality. And we can see that the sum of these blue numbers is strictly greater than sum of the red numbers, but that contradicts quadrangle inequality, so that cannot happen. So the leftmost part was important because we wanted this inequality to be strict. It would still work if we would take rightmost minimum, but it can be true that it is possible to choose some positions of minimums in each row so that this doesn't hold. But if we do it in some consistent way, like almost leftmost or almost rightmost, it will be true. And like how to use it to do DP optimization is out of the scope of this video, but check out links in the description to see how that can be used. Let's go back to our equality problem. Doing all the same steps, we can show that if we have equality for 2x2 squares, we can have equality for any rectangle. Let's say that we fix elements in the first row and first column. Then we are able to find all the other elements. If we want to look at elements at element aij, we can look at this rectangle, and for its diagonals, the sum of these two elements should be equal to the sum of these two elements. So our aij should be equal to aa1 plus a1j minus a11. This is a bit asymmetric, like we fixed first row and first column for some reason, and everything else is decided. Let's make it more independent of first row and first column. We can introduce values ri for rows and cj for columns, and just say that element aij in the grid will be equal to ri plus cj. If we have quadrangle inequality, this is true, because, for example, we can say that these elements are ri, c1 is 0, and the remaining elements of the first row are cj from second to h. And it is easy to see that, not these elements, but cj is the difference of this element and a11, sorry. It is easy to see that we will actually construct the same grid. What we want to prove is that it is like if and only if situation. So we want to prove this lemma that if the grid satisfies quadrangle inequality, the grid satisfies quadrangle inequality if and only if we can choose ri and cj such that each element is defined as ri plus cj. We have already proven this direction. Like if quadrangle equality holds, then we can choose ri and cj. In the opposite direction, it is really simple. Just take a rectangle and calculate the sums on the diagonals. Obviously, in both cases, it will be just sum of values for two rows and two columns. So they are equal, so quadrangle equality holds. There is also one small thing we should think about. Like we have to make sure that all our elements. We have to make sure that all the elements in the grid are non-negative, and since we know that we can do quadrangle equality if and only if we can choose these numbers, we now want to choose these numbers instead of actually filling all the grid. So we want to transfer this property into a property on ri and cj. And it is natural to think that we should just have properties that ri is non-negative and cj is non-negative, right? Like this is this should be non-negative, and it is the sum of ri and cj. If both of them are non-negative, then we are good. And it looks like we should be able to put both of them non-negative, and this is just a simple argument to verify that. Important thing to notice is that for any number delta, we can subtract it from all r's and add it to all c's, and that will not change any element in the grid, because element in the grid is ri plus cj, and so we decrease this by delta but increase this by delta, so it's like minus delta plus delta. That doesn't change the element. And we want to prove exactly what I said. For a matrix with quadrangle equality, if it is possible to choose a and j non-negative, if and only if it is possible to choose non-negative ri and cj. If it is possible to choose ri and cj, then we can obviously get non-negative elements in the grid. Otherwise, we know that the matrix satisfies quadrangle equality, therefore there is some values Ri and Cj. Let's take them. They can be negative right now, but we can try to make them non-negative using this change. And well, the idea is just to look at the minimum of Ri and minimum of Cj. They will still stay minimums when we apply this operation. And if the sum of those minimums is strictly negative, that means that the element on intersection of that row and that column is negative, and that contradicts that all the elements are non-negative. Otherwise, we can shift them to be minimums non-negative, then all the elements are non-negative, and this is just like an exact way to do that. Nothing smart or interesting here. I'll give you like half a minute to read that. Alright, we have reduced the problem to the following. Check if it is possible to choose non-negative values Ri and Cj for each row and column, such that for n given cells in the matrix, the sum of the corresponding row and column values is the given value for that cell. It seems like it's just a different problem and it's not much better. Well, it is. It is much better if you know how to work with grids. Not always, but sometimes you should look at the grid and see a bipartite graph. And in particular, a bipartite graph in which the left part is rows, the right part is columns, and for every cell there is an edge that connects the row and column on intersection of which the cell is. So for example, for this grid we have 3 rows and therefore 3 vertices in the left part, 2 columns and 2 vertices in the right part, and for every cell there is an edge. So for this green cell A11, this green edge between R1 and C1, pink cell A22, pink edge between R2 and C2, and for this blue cell A31, blue edge between R3 and C1. So that is the graph we will build. And now in terms of this graph, we are given some edges with numbers written on them, and the question is, can we write the numbers in the vertices such that those numbers are non-negative, and for every given edge the number on the edge is equal to the sum of the numbers in the vertices. Connected components in this graph will be independent. And if we know one number in the connected component, we can run DFS and find all of them, because if we have the edge and we know a number on one end of that edge, we can deduce the number on the other end, because we know the sum of endpoints of that edge, and we know one of the numbers in the endpoints, so we can deduce the other one. So for example, if we look at this grid, we can build this graph. And if we put like 0 in this vertex, then with DFS we will deduce that it should be 0 in this vertex. Then this edge has some 4 and we have 0 here, so there should be 4 in this vertex. And this edge has 2, this is 0, so this vertex should have 2. Moreover, if we say that in this vertex we actually say the value is delta, then using the same DFS we can understand that it should be 0 minus delta here, 4 plus delta here, and 2 minus delta here. And since our graph is bipartite, each time we go through the edge, if we had something plus delta, we will have something minus delta, where something is constant depending only on the vertex. So for if we start in the left part, for all the vertices in the left part, they will have some value plus delta, and for all the vertices in the right part, they will have some value minus delta. So for every connected component, we choose any vertex, put 0 plus delta there, then traverse the graph using DFS and find which numbers, like number plus delta or number minus delta, should be written in each vertex. They can be cycles in our graph, and for example, in this case, like this grid, which is, we remember, as the sample in which in this and this 2x2 squares, like we deduce different numbers for this cell, so that's bad. We get this graph, and if we start like 0 plus delta here, get 0 minus delta, 3 plus delta, 1 minus delta, but then there is this edge, and we already know both numbers in the endpoints, like it should be 0 plus delta here and 1 minus delta here, and their sum is just 1, because deltas will cancel out, and that will always happen like that, right? Because all the edges are between left and right part, and in the left part we always have something plus delta, and in the right part we always have something minus delta, so they will cancel out. But on that edge we have 2 written, so that just says that it's impossible to do. And we knew that actually, like, it is impossible to do it for this grid. So we are doing DFS. If we visit a vertex for the first time, we can deduce what is the value in that vertex. If we get an edge that goes to a vertex that we have already visited, we should check that the value written on the edge is actually equal to the sum of the values on the endpoints. And if it is not, then the answer is just no. Okay, and now we should check that it is possible to assign non-negative values, but all we can choose is delta. So we have Ri plus delta for all the vertices in the left part, Cj minus delta for all the vertices in the right part, and we should check if it is possible to choose delta such that all of those values are non-negative. But we can only choose like minimum of these values and minimum of these values, which will be delta plus minimum of Ri and minimum of Cj minus delta. They should be non-negative, and from here we can get this bounding delta from both sides. So that delta should be at least minus minimum of Ri and at most minimum of Cj. And once again, look at the samples. So in the first sample, we found all the values, and now delta should be at least -4 and at most 0, which is okay. And in this other sample, from this grid, we build this graph, and we remember that it should be -1 here, so it's impossible. And the values in all the vertices we got from GFS as follows. And thus we get that delta should be at least 2, but at most 1, which is impossible. That's the solution. It works in linear time. And I think it is very beautiful. It has two big parts, kind of understanding that there should exist Ri and Cj, and then the truth about grids being bipartite graphs, which is a really cool idea that can be used in a lot of problems. That's it for second episode. Thanks for watching.